Welcome to my video lecture. This is an Amarnath, Assistant Professor in Mathematics, Science and Humanities Department, MLR Institute of Technology. Under the course Linear Algebra and Calculus, I am continuing the part, that is a last topic, quadratic form, that is a part 1 I am going to deal. So, just in the previous lecture, we have discussed about the diagonalization of real symmetric matrices. If it is a symmetric matrix, A transpose is equal to A is given, how to do the diagonalization, that is called diagonalization of real symmetric matrices. Now, present lecture related to the matrices, that is one of the important topic we discuss about quadratic form. So, what do you mean by a quadratic form? How to write a matrix into quadratic form? How to convert a quadratic form to symmetric matrix to quadratic form? This we are going to discuss. First of all, what is the definition of the quadratic form? Here clearly I gave the definition: a homogeneous expression of the second degree in any number of variables is called a quadratic form. Homogeneous expression. Homogeneous means the degree of the each term in the expression must be equal. Then it is called a quadratic form. In any number of variables, it may be 2 variables, it may be 3 variables or 4 variables. Clearly I will explain with the example. Let us say in 2 variables first, x square plus y square plus 2xy. It is a quadratic form in 2 variables. How can we say it is a quadratic form? See, the degree of the each term, x square degree 2, y square degree 2, 2xy, x degree 1, y degree 1, again that is 2. It is a second degree homogeneous polynomial. Second degree homogeneous polynomial. Right? That's why it is called as a quadratic form. Right? In 2 variables it is. Which variables? X and y. Let us take 3 variables, x, y, z. Let us say 3x square minus y square plus 3z square minus xy plus 2yz plus 2zx. See, it is a second degree polynomial in homogeneous, that two homogeneous and second degree, these two conditions, one is homogeneous and second degree, but is in 3 variables, it is in x variable, y variable, z variable. This is whereas only x and y. In 2 variables, 3 variables, 4 variables and n variables also we can write the quadratic form. This is a quadratic, the word quadratic gives second degree, and homogeneous, degree of the each term must be second degree. See, x square 2, y square 2, z, these 3 are called square terms along with the product terms. Maybe sometimes product terms may be absent or may not be there. So, x y second degree, x power 1, y power 1, y z 2 y z, y power 1, z power 1, 2 z x, x power 1, z power 1. So, this is a second degree polynomial in 3 variables. So, this is also a quadratic expression. Similarly, we can write in 4 variables, we can write in 5 variables or any number of variables, we can write the quadratic form. What is the key point to be remembered? That is, it must be homogeneous and second. Sometimes it may have only square terms, that is x square plus y square plus 2z square. See, only square terms, even though it is a quadratic form. Sometimes it may have only product terms, xy plus yz plus zx. It is a second degree homogeneous. So, it is also a quadratic form. Like that, we can identify the quadratic form. Now, this related to this quadratic form, we are going to change into the matrix. Our part is a matrix part. Means quadratic form we need to convert into a matrix. How to convert? Then what are the properties, that all we discuss. Now, so every quadratic form corresponding to a real symmetric matrix we can write. So, before that, so quadratic form general we have an expression, Q is equal to x transpose Ax. Definitely this will give quadratic form. How, sir? This A must be here. This is a quadratic form formula, x transpose Ax. In how many variables you want the quadratic form? And suppose A is a 2 by 2, 2 variables, 3 by 3, 3. Suppose let us say A is a symmetric matrix. Here A must be symmetric. We have theorem statement. In that statement we have that is A is a symmetric. Here we are not discussing about the theorem. quadratic forms related we are discussing. Suppose A matrix is there, suppose 1 2 1 2, suppose it is a 2 by 2 simple symmetric matrix. So 1 2 first row 1 2, so 2 1 2 1, it is a clearly symmetric. It is a symmetric matrix. Then x, let us say 2 variables, x is equal to 2 variables, let us take x1 x2. Then what I am saying, quadratic form will give x transpose x. X transpose means here you write x1 x2 and A. A means 1 2 2 1 and x, x1 x2. If you multiply these 3 matrices, how to multiply? So here x1 into 1, row versus column, x1 into 1 x1 plus x2 into 2 2x2. Next, second x1 into 2, so here it is a 2 cross 1, 2 rows, and this one we can multiply and we can write x1 plus 2x2 and x second row, first row x1 into 1 and row versus column x1 into 1 2 into x2. Multiplying these 3 matrices we can get the quadratic form that we are explaining very clearly here. Just look at this one. So otherwise you can write x1 into this x1 square, 1 x1 square, next plus here 2 plus 2 4 x1 x2 and 1 x1 x2. Otherwise we write again in the another slide clearly. Right. This here I will explain how to convert into quadratic form and symmetric form. This is about the real symmetric matrix. And every quadratic form can be converted to symmetric matrix and vice versa. Every real symmetric matrix can be converted to quadratic form. So one quadratic form is given, then how to convert into a real symmetric matrix. Then how that quadratic form, let us check one quadratic form related to the real symmetric matrices. Then I will take the one quadratic form which is a second degree. The second degree form matrix we can take x square and y square and we can write, let us take one quadratic form, x square plus y square plus 2xy. It is a second degree quadratic form. This I want to convert into the real symmetric matrix. Then how to convert means, here I am small shortcut I am telling here. Let us take xy, let us take x and y. Now it is a multiplication, x into x corresponding element x square, x into y xy, and y into x xy, again y into y y square. Right, here x square is the square terms are along the diagonal, remember, and product terms are other places. Now is a symmetric matrix to related to that. How to write means, first write the coefficients of the square terms along the diagonal. So x square coefficient 1 here and y square coefficient 1 here, and xy here, xy term here and here, xy coefficient how much here 2, since but you are writing in 2 places, that's why make it to half. So xy coefficient is 2, 2 divided by 2 1, so write in 2 places, xy we have 1 place here, 1 place here, right. So this is symmetric matrix 1 1 1 related to this one. So this quadratic form is converted to symmetric. It is a simple one. Suppose I will take another one. Suppose we have 3 variables, that is very important. Most of the problem related to 3 variables. Then x square minus y square plus 2z square minus 6xy plus 3xz, right, and plus xy xz and yz 4z, let us say. It is also a quadratic form in 2 variables, in 3 variables x, y, z, all are of the second degree. It is a homogeneous second degree polynomial, right. So how to do this one? 3 variables, same process. Instead of 2, you take 3 variables x, y, z, x, y, z, so that you will get the corresponding elements position. You will get x square, x, y, x, z, y into x, x, y, y into y, y square, y into z, y, z, z into x, x, z, z into y, y, z, writing in the proper order. z into z, z square. We can write yz or we can write zy. We can write xz, we can write zx. It's not a matter, right? So the positions clearly along the diagonal square terms. Every time this happens, right? Now, what is the symmetric matrix for this one? Symmetric matrix related to this quadratic form. How to write this one? A is equal to, right? How first what to do? Enter the diagonal elements coefficients along the principal diagonal. Here x square coefficient, y square coefficient, z square. See here x square coefficient is 1, enter in plus place. Y square coefficient is minus 1, second principal diagonal, and 2 z square coefficient is 2. First you write the principal diagonal elements, then about the next xy coefficient. In xy we have two places, here I have rounded. What is the coefficient of xy? Minus 6 divided by 2, because we need to write in two places. Minus 6 divided by 2, that is minus 3. Write here xy position, here xy position. Next, the xz position, first row third element, here third row first element. These are the xz positions. What is the coefficient of xz? 3. 3 make it half. There is no rule, every time it will be integer, it can be a fraction also. 3 divided by 2, you write 3 by 2. Here also you write 3 by 2. Next, yz, second row third element, third row second element. This is yz. What is the coefficient of yz here? This is a 4yz I am taking, 4yz, 3xz, 4yz you take. So 4yz coefficient is 4. Then 4 divided by 2, make it half. So 2, 2. Okay. So 3xz is a 4yz. So look at this one. Is it symmetric or not? Clearly it is symmetric. How can we check it is symmetric or not? First row 1 minus 3, 3 by 2. First column 1 minus 3, 3 by 2. First row is equal to first column. Second row minus 3 minus 2, 2. And second column minus 3 minus 2, 2. Third row third column. Third row 3 by 2, 2, 2. Third column 3 by 2, 2. Definitely if you transpose, A transpose is equal to A you will get. Means clearly it is a symmetric matrix. So this is a way to convert a quadratic form to symmetric matrix, because in coming problems when we are doing the quadratic form related problems, he will give quadratic form that must be converted to matrix, then only we can do the diagonalization or transformations we can do. That's why here clearly I am explaining how to convert the quadratic form to symmetric matrix. So once again, along the principal diagonal, element the coefficients of the square terms, x square, y square, z square, then each product term coefficient divided by 2. So here 3 by 2, here 4 by 2, minus 6 by 2, write in appropriate places. How to get the appropriate places? Just do some rough work here, x, y, z, so that you will be identifying the proper positions of the elements. So like this, any quadratic form can be converted to symmetric matrix, and any symmetric matrix can be converted to quadratic. That also possible. That also we discuss here. Right, matrix of quadratic form. So if a matrix is given, how to convert it to the quadratic form? Each matrix here clearly it must be symmetric matrix, then only we can convert it to quadratic form. Let us take a symmetric matrix. Symmetric matrix. What is a symmetric matrix? Let us take one symmetric matrix, 3, 0, 2. 3, 0 to first row, first column we should write equal, then remaining elements minus 2, and here suppose 6, here 6, and suppose here I am writing 0. Is it symmetric? Definitely. 3, 0, 2, 3, 0, 2, first row, first column, 0 minus 2, 6, 0 minus 2, 6, second column, second row, 2, 6, 0, 2, 6. Clearly it is a symmetric, such as A transpose is equal to A. I want to write the quadratic form related to this matrix, right? Let us take this one, quadratic form. Now first write the diagonal elements. We know the diagonal elements coefficients are square terms. 3 into x square, you can take x, y, z, you can write x1, x2, x3, anything you can write. I am taking the variables, 3 variables, it is a 3 by 3 matrix, I am writing in x, y, z. Some authors can write x1, x2, x3, anything is okay. Any number of variables x, y, z, x1, x2, x3, p1, p2, p3, anything you can take. Now 3x square, first diagonal, second minus 2 into second one, y square, 0 into z square. So, or simply you can write 0. Next here 0 plus 0 xy portion, 0 xy, just to make you understand I am writing, that is 0 xy. Next this is x z, first row x, third column z, x into z, x z, 2 plus 2, here 2, here 2, 2 plus 2, 4 x z. Next it is a second x and it is a z. So far it is a y and z, this is x, this is y, this is z, y into z. So here 6, here 6, 6 plus 6, 12. So here y and third column z, that is 12 yz. Finally you can write 3x square minus 2y square, this is 0, this is 0, and remaining 4xz plus 12yz, right. So clearly it is a quadratic form. How can we say quadratic form? Second degree, x square, y square, xz, yz. Okay, it is a quadratic form. Then let us think about the one more example in 2 variables or 3 variables. Suppose he has given, let us take 4 variables, right. Symmetric matrix, suppose 1, 2, 3, 4. 1, 2, 3, 4, right. Diagonal elements can be anything you can take, 0 I am taking. Next 6, 2, here also 6, 2, so that you will get symmetric matrix. Here diagonal elements anything you can take, 2, and here minus 4, here minus 4, and here 8. So look at this one, 1, 2, 3, 4, 1, 2, 3, 4, 2, 0, 6, 2, 2, 0, 6, 2, 3, 6, 2 minus 4, 3, 6, 2 minus 4, 4, 2 minus 4, 8, 4, 2 minus 4, 8. Corresponding rows and columns are equal. First row, first column, second row, second column, is that equal. So clearly it is A transpose is equal to A, right. So then we can write it as a symmetric matrix for a corresponding symmetric. You want in which variable? Let us say I want to write in 4 variables. So let us say x1, x2, x3 and x4. In 4 variables I want to write. First again you check the principal diagonal elements. Now again 1 into first one square, x1 square, 1 x1 square, x1 square. Next second one, x2 square is 0, you no need to write. x3 square into 2, third diagonal element, 2 x3 square. Next x4, x4 coefficient here 8, 8 x power 4. Okay, that is a square terms along with the product terms. So here how to do product terms here? First one is x1, this is x2, this is x3, this is x4, and above elements x1, x2, x3, x4. Now here second position is these 2 positions, x1, x2. So 2 plus 2, 4, 4 you can write 4 x1, x2. Next third, this is x1, x3 here and here, that is we can write 3 plus 3, 6, 6 x1, x3, right. Next here 4, here 4, 4 plus 4, 8. Which element? That is x1 and x4, x1, x4 combination. Next we have 2 more terms here. See, this is x2 second row, x2 and x3. This is 6 plus 6, 12, 12, and this x2 multiplied with x3. You can write as a product x2, x3. The last one here 2, 2, 2 plus 2, 4, and the term, which term it is here? This 2 and 2, x2 with x4 and x2, x4. Here x2, x4, here x2, x4. That is 2 plus 2, 4 x2, x4. See, so very easily we can convert the quadratic form in 4 variables also, symmetric matrix to real symmetric to quadratic form to real symmetric matrix. So once the student is able to understand this one, easily we can do the problem related to the quadratic forms. It can be 2 by 2, it can be 3 by 3, or it can be 4 by 4. So clearly here we have shown the problems. Now in this section we have discussed about the quadratic forms very clearly. And what do you mean by quadratic form? A second degree homogeneous polynomial is called quadratic form, and how to convert a quadratic form to symmetric matrix, and how to convert symmetric matrix to a quadratic form. So, in the next lecture, what we are going to discuss about the quadratic form properties, especially rank, index, signature and the nature of the quadratic form. That will be the next video lecture. Thank you.